We're going to talk to Steve about some of the aspects of the bioprinters. We must be able to commercialise and complete the whole package in order to address the clinical challenges that are in front of us. Hi, Steve.
Good afternoon.
So Steve is heading up our additive fabrication capabilities here at Tricep, and he's going to introduce us to some of our capabilities. It's a capability that we like to call printing printers. So tell us about that, Steve.
So we've been very fortunate. We have a range of additive fabrication tools, and we've recently been able to expand on that set of tools. This is just one of the new printers we have. It's a Mimaki 3D printer, allowing us to print components in full color representations. And that's now allowing us to give much higher level of details to our collaborators and our commercial partners to get real realizations of the parts that they want to be able to produce. These systems are then enabling us to print new components for new printing systems, and we'll be able to run you through a couple of those systems right now.
Of course, all of these projects we're going to look at are driven by real clinical need. I mean, we're very fortunate, aren't we, to be able to work with clinicians all around the country who are really defining the challenge with us, defining the plan and implementing the plan, and then helping us in terms of translation.
That's the real driver behind what we're doing, and it's giving us great encouragement to work outside of just doing research for the sake of research and being able to treat real clinical needs. And this is one such example. We're referring to this as the iFix pen. This is a device that allows us to deliver media or deliver two materials straight to a corneal ulceration in the eye, allowing us to treat that corneal ulceration, and in either the domestic environment or an overseas environment to be able to limit the chance of infection and ingress into the eye.
So the bio-ink is obviously an important part of this, and that ink has been designed to be compatible with the eye, to be transparent and to facilitate the healing process. And then I guess that the hardware, or the iFix pen, was designed around the requirements to deliver that bio-ink.
That's exactly correct. And the reason why this is, we always see these delivery mechanisms as tools. They're allowing us to take that fundamental material, the critical therapeutic material, and deposit it in the structure that's required. And this is one primary example where we're taking two materials, mixing them in a custom tip, allowing those two materials to cross-link and gel and be able to adhere onto the eye surface.
And it's been great to work with the clinicians as well, just on practical aspects of the ergonomics, how you hold it, how you deliver it.
And I'm probably holding it incorrectly as we look at it. I believe it's to be held in that manner. Right. But this allows us to refine that. And with the set of tools that we have here, it's very easy to go into an iterative process to refine the structure, refine the ergonomics of the structure so that they have better use of it in practice.
And I guess another thing about Tricep is that we'll go that step further. Not only will we develop the prototype, but we will make sure that that prototype is ready for manufacture by working with commercial partners to do that.
Again, that's a huge advantage of this facility, and building on our existing commercial relationships through linkage projects that we've had in operation for many years, and defining what really can be manufactured at scale. Yeah. So we have, obviously, as we're designing components, we have to keep in mind design for manufacture rules and larger scale injection molding rules, which would be the typical manufacturing processes that we use. But also being able to take our customized prototypes and put them into more complex stages. So the example case of a handheld device is ideal for a practical use in a clinical environment, but for us to characterize that device, to have fine control of the device as we're going through our experimental protocols, it's ideal to be able to transfer and mount the system into a 3-axis stage or even a multi-axis stage to allow us to have fine control over the scaffolding structures that we produce, to then be able to determine the repeatability and the consistency of the printing system that we've developed.
Yeah, brilliant. Well, that's brilliant. I mean, so there must be a whole suite of these that we're involved in developing now.
There is now. So the iFix pen is one of the earlier, simpler examples where we've got two materials that are being extruded simultaneously and mixing at the tip. Another example case, which has a slightly higher level of complexity, is the Excelda pen. And the Excelda pen...
This used to be the BioPen?
That is correct.
Right. Excelda sounds much better.
It does. It's undergoing a rebranding. So with the Excelda pen, we have a slightly more complex extrusion geometry. This is a coaxial extrusion geometry, where we would have an inner core and an outer sheeting of material, allowing us to maintain cells within the inner core and then have a protective outer sheeting during the actual extrusion process. Obviously, this tip is then a bit more complex, and through some of the technology that we have here on site, we've been able to develop a robust, refined structure with a complex internal geometry that's been produced out of titanium alloy. So that's easily cleanable, easily sterilizable, and reusable in our preclinical trials.
So how did you make that?
So the design was done in-house. We optimized the internal fluidic pathway through a CFD analysis, and we were then able to produce it using metal additive fabrication. So the actual process is referred to as selective laser melting, allowing us to produce features with a minimum wall thickness in the order of 200 microns.
So it's printed on a metal printer, a 3D metal printer.
That's correct. So a 3D metal printer, we're very fortunate to have two of these systems available to us. The first is would have a cylindrical build volume, a 70 millimeter diameter tray with a maximum build height of 74 millimeters. The newest, most recent system that we've added to the facility is a Concept Laser 200R. That allows us to have a print volume of 100 millimeters by 100 millimeters by 100 millimeters. So a liter of volume that we can print within. We can print in a range of different metals. Stainless steel and titanium will be two of the most common materials, allowing us to produce high resolution, low surface roughness components that are ideal for customized prototypes.
So some of these structures must be really difficult to make at all using conventional manufacturing approaches.
Well, that's absolutely correct as well. So what you can do is, if you actually look at the supporting structure, and this is sacrificial supporting structure, we're able to make these intricate geometries, open porous lattices that in our mind are ideal for complex electrode structures, or indeed the production of complex fluidic geometries.
Yeah.
Okay.
But that's amazing. I mean, so you really are printing printers.
Well, we're moving on so that we, instead of having our handheld devices and integrating those into commercial type platforms, we're actually developing our own customized platform that's allow us to have additional functionality to incorporate additional extruder or deposition techniques simultaneously, as well as cross-linking methods. So in this example case, the 3D ED, we're able to have two materials being simultaneously coaxially extruded with temperature management on both of those materials, and also the feature or the capability to be able to cross-link those materials as they're being deposited.
And this educational printer is an important part of our online teaching program that we're putting together. As you know, we have a graduate certificate in biofabrication, which is available online now. And that is actually the coursework or that's necessary to move on to the Masters in Biofabrication. And it's exposure to all of these types of printers that really give high-level, state-of-the-art training in 3D printing, isn't it?
That's right. And within this small package, our prospective young engineers and bioengineers have a range of tools, a range of capabilities for them to learn. So from the fundamentals of the 3D positioning systems right through to the development of the manual or mechanical extrusion mechanisms, temperature management, to allow us to see what happens to our different materials under different temperature conditions, but also under different printing conditions or extrusion diameters.
And of course, building the printers is in itself a great dimension to the training, isn't it? We had a number of summer scholars working here with the team at Tricep, who actually were the first, I guess, to build the 3D ED, and we're learning from that experience and how we can use that building of printers as a training aspect.
Yeah, and it's been a training session for us as well. Those students were able to identify the benefits for them in what they were able to grasp from our initial developments, and what they were able to contribute towards it, so to how we could refine the design to improve our design of manufacture and design of assembly.
Great. So thanks for giving us that amazing insight into how we're using conventional 3D printers to create a range of customized printers, which is helping us to address important research challenges in the medical sphere, but also helping us to build new tools for training the next generation of biofabricators.